Hey guys, feature engineering. Today we are diving into a crucial aspect of machine learning, feature engineering. We are starting a new series, a playlist of videos to understand everything about feature engineering, explaining all the different methods of feature engineering with demo with an example. It's often said that good features, that is good data, are what makes or breaks a model's performance. For now, let's explore what feature engineering is all about and how it can supercharge your machine learning projects. This video, we will deep dive and understand what is feature engineering, why feature engineering, and benefits of feature engineering. The third thing that we will talk about how the techniques and the strategies in feature engineering. And lastly, one of the simple way, an example on feature engineering so that you can also understand how it really works. So stay tuned and make sure to watch this video till the end, and let's get started. Hey guys, welcome to AI with AI. This side, Asif Imnad. Let's start with an amazing story here. Imagine you are an owner of the toy shop. Imagine your suppliers dumping all the toys you requested into a one room while you were setting up a gift shop, and it's going to look something like this. As you see in the image, it's a complete chaos. Imagine yourself standing in front of this enormous pile of toys, trying to locate the ideal gift for a kid, for a customer. You know that in the pile of these toys, in this chaos, what the kid is asking for. Now, imagine a second scenario. You first organize the toys before opening up the shop. You might want to group the toys into categories, or you might even choose to replace some broken toys with the newer ones. You arrange the toys in a certain way so that you can find them easily. You might even realize some toys that you have asked for were missing and take the necessary actions even before the customer comes into your shop. That sounds like a more organized and sensible approach, right? Well, when we build machine learning models, in most cases, the data we deal with looks like this unorganized chaos of toys. This data need to be cleaned up and pre-processed before it can be put to use, and this is where feature engineering comes into play. So, in simple words, it is a process that aims to bring chaos to orders. Let me get straight to the point. We all know machine learns from the data. Input we provide to the model is the data. But imagine if input data given to the model is not pure, it is not organized, it is not a quality data, it is not superior. Then how can we get the better model? How can we expect that the model precision and the accuracy will be as per expected? How can we increase the accuracy and the precision of the model? And also by the research, it is found that, as you can see in the image, most of the time is spent on cleaning and organizing the data, collecting the data, mining the data, and very less time is spent on refining algorithm and training and testing your model. So once you have quality data, organized data, pure data, then it becomes very easier for you to create a high quality, accurate models. When feature engineering activities are done correctly, the resulting dataset is optimal and contains all the important factors that affect the business problems. This will result the most accurate predictive model, and the most useful insights will be produced by your machine learning model. And creating of successful machine learning model looks something like this, right? You get the data from different sources, so you have a raw data which is unorganized, it is chaos, data is missing, we do not have much columns. And that's why we need to clean and transform the data. That means collect the features, look for the required features, make the data machine learning friendly. So before we go to modeling, where we provide our input, where we provide data to a machine learning model, before that, make the data machine learning friendly. And this is the really important step in machine learning or in data science journey. So feature engineering is the process of transforming raw data into features that are suitable for machine learning models. In other words, it is a process of selecting, extracting, and transforming the most relevant features from available data to build more accurate and efficient machine learning models. The success of machine learning model heavily depends on the quality of the features used to train them. So feature engineering involves a set of techniques that enable us to create new features by combining or transforming the existing ones. These techniques will help to highlight the most important patterns and the relationships in the data, which in turn helps the machine learning model to learn from the data more effectively. If this is very much clear to you, let's talk about what are the steps involved in feature engineering. But before we proceed and discuss in detail, if you're new here, don't forget to hit that subscribe button and the bell icon so you won't miss our latest videos on AI. We have recently started this series, so there are a lot of things that we are going to talk about 10 to 15 videos we will be creating only on the feature engineering. We see you're watching our videos, but 90% of you are not yet subscribed. We put a lot of efforts creating these videos for you free, so keep us motivated by liking and subscribing, so in return YouTube algorithm will help us reach more audience. Did you subscribe and like? Thank you. Now let us see what are the ways to perform feature engineering. The steps for feature engineering vary as per different machine learning models and the data scientist. Some of the common steps that are involved in most machine learning algorithms are as you see on the screen. The first one is definitely the most important and the simplest one, which everyone must think of doing, is a data cleaning. The second thing is data transformation. We'll talk about this in short. The third thing is feature extraction. The fourth is feature selection. And the last one is feature iteration. Let's talk about this one by one quickly. First one, a data cleansing. Data cleansing, also known as data cleaning or data scrubbing, involves identifying and removing or collecting any errors or inconsistencies in the dataset. This step is important to ensure that data is accurate and reliable. In short, we remove nans, nulls, empty spaces, empty rows which are not required. In short, we will be looking at unnecessary variables or the symbols which will be embedded in the columns, like question mark or nan values or the spaces, whatever. You might think of cleaning that data before you feed that data to the machine learning model. So that's simple data cleaning. The second is data transformation. A data transformation is really important. It involves converting and scaling variables in the dataset to make them more useful for machine learning. This includes the techniques like normalization, standardization, and even the log transformation. Just to give you a simple example, machine learning doesn't understand categorical data, right? If you have a temperature given as a categorical input, let's say high, medium, and low temperature, then machine doesn't understand that categorical data. So in this situation, we need to transform those characters to numbers. So I might think of assigning some numbers to high, assigning some numbers to medium, and assigning some numbers to low. And the other example of data transformation can be, sometimes you might not have a complete data. I mean, you might have some fields of the rows empty. Data might be missing for a certain columns for a specific row. So if data is missing for certain rows, what values you should add? So in such scenarios, you can use normalization techniques, and you can also use statistical ways where you can find mean, median, or mod and the average of all the data points and feed the same. So that is data transformation. Don't worry, we are going to see all these types along with the techniques in detail with the demo in the future videos. Currently, we are just looking at the different steps involved in feature engineering. Okay, the third is feature extraction. Feature extraction involves creating new features from the existing variables in the dataset. This can include techniques like very famous one, that is PCA, principal component analysis, a text parsing, and even image processing. So just to give you an example, you might not have all the required columns or the complete data which can make a sense and which can be fed to the model. Let's say you just have two columns. One is timestamp, but only from the timestamp you can extract more columns, more features, right? From timestamp you can extract hours, you can extract days, you can extract weeks. So feature extraction is all about creating more columns or reducing columns so that machine learning actually makes the sense and finds the pattern in the data and create the better machine learning model. And the really good example for feature extraction we have seen in the last video, where isolation forest dataset we have worked with, a New York City taxi data, where we did feature extraction before feeding that data to isolation forest models. So check that video. I will keep the link in the I button above, and also in the description you can find it out. So the initial part in that video is all about feature engineering and feature extraction. You can have a look at that. The fourth one is feature selection. Feature selection involves selecting the most relevant features. Sometimes you may have a huge data, but all that data might be unnecessary, or all columns might not be required. So fetching only required data, fetching only required columns is really important. And by selecting only the specific features, you can not only save the training and testing model, but you also make your machine learning model to take the proper decision based on given a specific data, and it is not looking for unnecessary data. And the techniques that we use for this is a correlation analysis. correlation coefficient matrix is a really nice example of this. A mutual information and stepwise regression, these are some of the techniques used in feature selection. And we also have an amazing video created on correlation coefficient matrix to improve the machine learning accuracy. We discussed that with an example, with a demo. I will keep the link of that video in the I button. You can check that out that as well. Talking about the last one, which is feature iteration. Feature iteration involves refining and improving the features based on the performance of the machine learning model. This can include a technique like adding new feature, removing redundant features, and transforming features in different ways. Overall, the goal of feature engineering is to create the set of informative and relevant features that can be used to train a machine learning model and improve its accuracy and performance. The specific steps involved in process may vary depending on the type of the data and specific machine learning problem at the end. I'm not saying that you have to perform all these steps. It depends on the type of machine learning model that you're creating, depends on the data, what you are using. So based on that, you have to make the decision that whether I need to transform the data, whether I need to extract the new features or use a feature selection method to get the specific relevant columns. And one of the technique that is used in feature iteration is bindings, and it is the process of grouping continuous features into discrete beans. This can help simplify the features and reduce the noise in the data. What it is, how it works, we'll see in the future videos. This is a really simple example to handle missing data, and we have used a feature cleaning technique which is called imputation method to work with the data. So here we have a very simple demo to handle missing data. The data set that we have used is Titanic Survival. We've already seen this beautiful movie performed by Leonardo DiCaprio and Kate Winslet, right? So we all know the story, what happened with the Titanic, right? So we need to get the survival predictions on the Titanic dataset. But before we do that, before we do the prediction, who can get survived? Whether it is a female survival rate is more? Does age has any effect on the survival rate? Does gender has any effect on the survival rate? But before we do that, before we feed that data to machine learning model, all we need to do is handle the missing data. That is feature engineering we need to do, right? So first let's import the required libraries. I'm importing pandas, numpy, seaborn, matplotlib. And we have also created different Python class missing data. We are importing it as ms. We will be using this ms further to use some of the functions from this class. I'll show you that class how it looks like. For now, let's load the dataset. So we have a dataset that is Titanic CSV. We are just loading the data and we are just looking at initial 8 rows. Shift enter. So this is how the data looks like, whether they survived, not survived. This is the Y column. 0, 1, 0 stands for not survived, 1 stands for survived. Passenger class, gender, age, CBSP, fair. We don't really need to go into that detail. We just need to clean the data, right? So from this I can see the 5th row is nan, right? So this is where I might need a cleaning of data. So first of all, let's check the missing values. So for missing values, I have used ms.checkMissing. This is our function and we have created our class which is missing data. Let me show you how it looks like. It is really simple. We have created our own functions to check missing values, to drop missing values, to add variable and denote it by na, impute na, that means add na with the arbitrary value, impute na with the average, impute na with end of distribution, impute na with random values. So these are the functions that we have created to clean the data, to work with the data. I'm going to upload this code on the GitHub repository and I will make it available for you. You can check that out in the pinned comment and also in the description box. You can download and try out the same thing. So for now, let's see how many missing data, how many missing values do we have. For that, I have used a simple function check missing and I'm going to check missing. I'm calling this check missing, and here I'm using pandas.concat and we are using a very simple function on the data, that is data.isNull.sum to get the field, right? 1, 2, 3, 4, how many fields we have null. And finally, I'm storing those values in the results by creating 2 columns. One is total missing and the proportion. So we need to see total missing fields for any columns that we have, right? So once we have new dataset prepared showing total missing values and the proportion, we are just printing it here. So let's see how it looks like. Let me execute this to see the missing values. So I can easily see that total missing for age is 177, whereas for other columns we do not have any missing data. Beautiful. I can also do the list wise deletion. So the very simple thing that I can do where I do not have any data, I can simply drop them, right? Wherever I have NA, NaN, I can drop those fields, right? For that I'm using drop missing. So let me go to drop missing and see what we have written here. I'm creating a copy of the dataset and then I'm using a simple function drop NA on the same axis, and in place is false because I don't want to save it back in the original dataset. I want to save it in the data copy, okay? And print that data copy, return that and print that, and let me see the shape now. So I have 714 rows now. That means 177. I have 714 rows now and 6 column. Let me see initially before dropping how many rows we had. For that I think we executed this. Let me see. So you see we did data.shape before dropping those NA and NaN rows, right? NaN fields. So we had 891 and after dropping we have 714. Similarly, we can perform many other operations like adding a variable to denote NA, arbitrary value imputation, mean median mode imputation. So all of this you can try out on your own. Currently this was just to understand what feature engineering means and how can we handle missing data. In future videos we are going to deep dive and see these feature engineering techniques in detail with the specific feature engineering technique. So make sure you subscribe to our channel and press the bell icon to stay connected. So now let's conclude this video. In this video we have discussed feature engineering for machine learning. We have covered the basics of feature engineering, including why feature engineering is important and some of the most common techniques and the steps involved in feature engineering. We encourage you to experiment with feature engineering to see how it can improve the performance of your machine learning model. Let's talk about the data, what data we are going to use. Let's understand the data. So the data which we have just have two columns, timestamp and value. This is New York City taxi data, okay? So during what time, how many taxis are booked? So this is a timestamp and number of taxis in demand. So if you see, data is in the interval of 30 minutes. Midnight, 12 o'clock, 12:30, 1 o'clock, 1:30, 2, right? So this is the count of the taxis booked or taxis in demand after every half an hour. So this is what the data we have, but we just have two columns. So a lot of feature engineering part we have to do on this data for sure, right? They have also given 5 events when anomalies might occur. New York City Marathon, which was on this date, then Thanksgiving Day, then Christmas Day, then New Year's Day, and in January 2015 a North American blizzard occurred during this date, which is 26th and 27th of Jan. That means what? Why these events are important? Either the demand of the taxis will be lesser because of the marathon, or because of the storm and the snow, everyone will be sitting at the home, so no taxi demand, right? So these are the dates when anomalies can occur. So let's see if we can gauge these anomalies using isolation forest, using our example. So this data, which is New York City taxi demand data, is a time series data. We have time given, right? So based on the time we have value, which is nothing but how many taxis are booked or how many taxis are in demand. So that's how it is a time series data. So first we need to import all the libraries. What libraries we are importing? NumPy, Pandas, Matplotlib, though we are not using this directly. HoloViews is something beautiful or a new way of visualizing data. So we'll be using HoloViews as HV library to visualize the data. You'll be amazed to see how beautiful graphs and the visualization it provides you. We are also using Bouquet and the HoloViews. These two libraries we are using for visualization. Then just ignore the warnings, right? Let's execute, shift enter. Going down, we already discussed the data. I have given some references and inspiration from where I'm able to create this example. By the way, don't worry about this notebook. I'll be providing you this notebook on the GitHub repository. I'll keep the link again in the pinned comment and also in the description, okay? So find that out. You can just simply clone the repository and use the way I'm using here. After importing the libraries, now we are reading the data, loading the data, New York taxi CSV format data, and let's execute this. Let's see first 5 rows, df.head. This is how the data looks like, which we have already seen. Timestamp and the value, time is given and value is given. So at midnight 12 o'clock, 10,000 taxis were booked. After 30 minutes, 8,000 taxis were booked. As time increases, after midnight, after 12 o'clock in the night, the demand goes down, right? This is what I can see here easily. So dataset has just 2 columns. That means a lot of feature engineering we will have to do to extract the information and find the insight. Now let's check the data type and let's perform some housekeeping to check the blank values and check the data type of the data. Shift enter. So I see there are no null values, no zeros. Data type is integer type value that we have, okay? And the date start and the end. and the date range is given here. So we have data for 214 days. Amazing. So here we are going to use HoloView and Bouquet library to get the data hourly, daily and weekly. hv.curve, which is HoloView.curve, will help me plot the curve, the demand of the taxis hourly basis, right? So hv.curve, again plot a curve for a daily basis, plot a curve for a weekly basis, right? So what are we plotting here? We are plotting hourly, daily and weekly New York City taxi demand. Let's execute this, and I'm using options. There are multiple options to customize this HoloView. So options function is used for the customization purpose. Let's execute this. Great. I see an amazing graph here, though it doesn't look like a curve as it is hourly data, right? It is not every minute data. That's why the curve is not so smooth, but this looks so pleasing. So we have data plotted for hour, for day and for week. So these are the different options that HoloView uses. So I have a pan by which I can move this. I have a zoom so that I can select the specific area. So I see a spike here, a taxi demand increased suddenly on some particular day which went till 40,000. I can zoom into this part by using this zoom in function. These are the interactive features that HoloView gives. Zoom in, zoom out, reset. Do you see that by hover over I can see the timestamp and the value for that particular hour? Similarly, I have a daily New York City taxi demand plotted here. Visually, you can easily say that there is some seasonality to the data. This is seasonal data, right? During night time, the demand goes down. During daytime, demand increases, goes down, increases, goes down, increases, right? So during night time, less demand of the taxis. That's very obvious. And on some days, you see taxi demand went really low. We have some anomalies here, either here. Look at this day in 2015. Taxi demand drastically went down, even below 5,000. And New York City is definitely not a small city. It is one of the most populous and one of the most tourist place in the world. And also I see on some of the days there is a spike, high demand of the taxis on certain days, right? So this will help me find the insights of the data. And also on the weekly basis, this is how the data is plotted. Okay, let's proceed further. Now let's do some feature engineering so that I can create some more columns like data frame hourly, data frame daily and weekly. I want more columns so that I can easily spot anomalies, or I can easily see when the demand is boosted or when there are lags. So I'm using a original dataset, data frame, resampling on hourly basis, find the mean and assign it to hourly variable. Same for daily and same for weekly. So we created 3 new columns. Let's execute these. Shift enter. Now I want to see a data for daily basis for Monday, Tuesday, Wednesday. I mean, rather than checking the value taxi demand every 30 minutes, I want to check how does the taxi demand looks like on a daily basis. Not only daily basis, also based on the weekdays. If it is a weekday or if it is a weekend, is there any change in the taxi demand? That's why I'm preparing a data frame for hour, day, month, year, month of the day, and I also have lag and rolling means. So lag will help you understand how much deviation we have from the previous day taxi demand. And rolling mean column is something like moving average. It will show you the average of last 7 days. So this is a rolling mean for last 7 days. Let's see the data frame, how it looks like. I'm plotting data frame.tell last 15 rows. Now you see I have more columns. Now I can easily see the more insights in the data. Timestamp, if you see, now timestamp is not hourly basis, this is daily basis, 17, 18, 19, 20, right? Also more columns like hour, day, month, year are added, and more importantly lag and rolling mean. So by looking at this lag, it will be helpful for us to see the anomalies. It will be helpful for us to see deviation from the previous days. Visually, I can see on this particular day the value of lag is very small on 27th and also on the 28th of January, right? 27 and 28, the value of lag is very small. That means it looks like an anomaly to me just by looking at the data. Do you remember initially when I discussed the data, I have shown you they have given us 5 major events which occurred on a particular day, like New York City Marathon. So in January, we can see on 26th and 27th, American blizzard happened because of storm, because of the snow. Taxi demand will be definitely smaller because taxis will be stuck, or because of the snow, no one wants to go out for sure. So that's why the value of lag is really smaller here. Great, that's the benefit of feature engineering. Let me do some more visualization. I'm just playing with HoloView library here. I'm drawing here a distribution graph to see value and the density. This will show me density versus value. Basically, this is a KDE, kernel density exploratory graph, right? Demand goes high, comes down, demand goes high, comes down, right? So this is what I can visually see here. The reason behind I used hollow view distribution graph is to see the demand of the taxis based on the weekday or the weekend. How the taxi demand varies during the whole week. Does taxi demand increases on the Saturdays or Sunday because of the tourist place? I don't know. I want to see more visuals, more insights. That's why I'm using hollow view distribution and plotting the data for whole week. You can see we are plotting distribution plot for Monday, Tuesday, for all the weekdays, right? Let's see how it looks like. Beautiful graph I see. To understand the data, I can select and unselect these days to see the taxi demand on a particular day. Let me see how the taxi demand looks like on a particular day. If I select Monday, I can see this graph here shows the taxi demand on Monday. Let me see it only for Saturday or Sunday. I will unselect all other days so that I can visualize only Saturday. So if I see Saturday, so this graph shows a taxi demand for the Saturday. I can easily see that the demand during the night time increases on Saturday. People are enjoying holidays, people are enjoying weekends. So the taxi demand during night time is more on Saturdays. And contradictory to this, on Sunday I see taxi demand is lesser because on Monday people wants to go to offices. So there is a less taxi demand during night time but more taxi demand during daytime, right? And highest taxi demand I see is on the Sundays only. If I see it for Monday, during a daytime a taxi demand is more. Same goes for all other weekdays. So this is the very useful insight information that I get here. There is a huge variation in taxi demand on Monday, Saturday and Sunday, right? So on Saturday people prefer more taxis during the night time, and on the Sunday taxi demand is the highest, and on Monday taxi demand during daytime is more. Now let's plot a bar chart for taxi demand group by weekday. For all the weekdays, how does the taxi demand look like? Show me it in a bar. So Monday, Tuesday, Wednesday, I don't see much of the difference here, but on Saturday I see maximum taxis gets booked, right? So demand on Saturday is more and demand on Sundays is bit lesser here. This is what I understand by looking at the bar chart. Let's proceed ahead. Let's see more insights, deep dive and see, is there any seasonality based on the hours? How the taxi demand varies during different time in a day. So let's execute this to understand taxi demand group by hour. So I'm gonna execute this, shift enter. You can see a New York City taxi demand hourly, right? 0 is midnight. After the midnight, taxi demand definitely goes down, and it is lowest 5 a.m. in the morning. For sure, people are sleeping. Then again after 5 o'clock, you can see a gradual increase in the taxi demand, right? Because people wants to go to office and visit some places, visit Times Square, so on and so forth, right? And the highest demand of taxis we see 7 in the evening. Let's see for every day in a weekday, how does the taxi demand look like? Hourly for all the weekdays. So this again gives me a really amazing plot. I can select and unselect whichever day I want for a specific day, let's say for Sunday, and let's see for Monday, just to differentiate a taxi demand for these 2 days only. On Sunday, this is Sunday, so on Sunday you see during night time after 12 o'clock, after midnight, the taxi demand is more, but on Monday taxi demand is less, right? In the midnight on the weekends the taxi demand is higher, whereas on other days, on the weekdays, the taxi demand is small. For sure, on the weekends people go out, enjoy, party and visit some clubs around, so night time taxi demand is more, weekday night time taxi demand is less. During daytime on Saturday and Sunday, taxi demand is less compared to other weekdays. On Saturday and Sunday, taxi demand is less during daytime. This is what the insight that I easily see using hollow views. Here I'm preparing data frame hourly and data frame daily, and let's see how does hourly data frame look like. You can see that on 31st of Jan 1920. So this is early taxi demand that we can see here. Simple, nothing much. I can use early data frame and I can also use daily data frame to identify anomalies. That's why we prepared daily and early data frames here. So in conclusion, in this video we have discussed feature engineering for machine learning, how to perform feature engineering on time series data, the famous time series data, New York City taxi data. We created multiple new features, hourly, daily and weekly columns to understand how the taxi demand flows during the weekdays and the weekends, And does time has any effect on the demand of the taxis? This is what we understood by performing feature engineering. Not only that, we have also seen how to better visualize the data using HoloViews and Bouquet library. Now we encourage you to experiment with feature engineering more to see how it can improve the performance of your machine learning models. So here we are talking about missing data and imputation. The process of replacing missing data with statistical estimates of missing values is known as imputation. So this is the data given by the researchers. Where do the data scientists spend most of their time? If you see, most of the time, 50 to 60% of the time, efforts are spent on cleaning and organizing data, and very less efforts are required for training, for refining algorithms, and so on and so forth. So quality data is what really matters to build the successful machine learning model. So what do you mean by imputation? The goal of any imputation technique is to generate a complete data set. Basically, wherever you see NAs, NANs, or incomplete data, we need to impute. We need to add a sensible data so that can be used to train machine learning models. And what are the different imputation techniques that we have? Let me talk about that quickly. So as you see in the diagram, we have two ways: statistics imputation and arbitrary imputation. So statistics is the most famous one and generally used. And for statistics imputation, we use mean, median, or mode. Mean, median is mainly used for numerical values, and mode is generally used for categorical variables. Wherever we have numbers, numerical values, we use mean or median, and wherever you see characters, categorical variables, we use mode, right? So if you have missing data in some of the rows for some of the columns, then we should add some sensible data, and we are using statistical way, and also we can use arbitrary way, but statistics makes more sense to impute the data. So if you don't know when to use mean, median, or mode, let me quickly talk about this in a short and we'll jump for the demo, right? So mean, median, mode. When to use mean, when to use median, when to use mode. Mean and median is nothing but averaging. So mean is best used when data distribution is symmetrical. As you see in the middle, this is data distribution, and you see it is symmetrical and there are no clear outliers. Data is not biased. Data is not asymmetric. So here mean fits best. So if data is not skewed, data is symmetric, I go for mean. I prefer mean. And if I see data is negatively skewed or positively skewed, I prefer using median. When data distribution is not symmetric and I see a clear outliers here. So whenever I get a data, I always practice to plot the data so that I understand the characteristics of data. I understand the distribution of the data, right? So based on that, I will decide whether I would impute mean, median, or mode. Mode is simple. We use mode for categorical data, for characters, right? The question is only about mean or median. I hope that's clear now. Now let's jump to the Jupyter notebook and see how we can perform the same. Alright, so here I am. This is the same repository which I have also uploaded to Git repository. The link of all the code, all the implementations that I am using here for the demo are kept in the pinned comment and also in the description. Please find that out. You can copy paste the same thing and try on your own. So I'm going to folder 0. Basically this comes before all the machine learning algorithms. So this is feature engineering. So I'll go to feature engineering, and we have already seen missing data. We have seen creating new features. Now I'm talking about mean, median, imputation. Let me open this notebook. In this notebook, our goal is to handle missing data using mean, median, and mode, right? So I'm gonna import pandas, matplotlib to plot some data, and train, test, split to split my data into training and testing, right? Shift enter to execute this. Then I'm gonna select some of the columns. The columns which I'm selecting are basically from house price.csv. So we're using a very famous data set here, which is housing price prediction data set, and specifically we are using some columns on which we want to perform imputation. And I'm reading house price.csv. Basically this is available within the data set. Let me show you where I have kept this CSV file. Okay, under this feature engineering, you should see mean, median, imputation Jupyter notebook, and under data I have house price.csv. This is the dataset CSV file that we are using for feature engineering. Let me come back to the Jupyter notebook and execute these cells. Let me select the columns. Let me load the dataset and also print the dataset head. Okay, so I have 1460 rows and 10 columns now. So you see lot frontage, overall qual. These are different columns which are available, and this is how the dataset look like. Remember that we have 1460 rows. We are using mean or median that we will use to replace NA, which are calculated on the training dataset. let me proceed. And what we are doing here, we are preparing our data, xtrain, xtest, ytrain, ytest. We are splitting our data into 30-70. Test data is 30% and 70% is training data, right? We don't want to consider a sales price for now, so we are dropping that column and random state 0, and let's print the data. Let's see how it looks like. So out of 1460 rows, now I have 1020 training rows and 438 testing rows, right? 9 columns because I dropped one column. Sales price I don't want to consider. This is our Y column, which is basically a prediction. Okay, that's why we dropped it. Let's start with finding the missing data. So to find the missing data, I'm simply using training data, and if it is null, show me the mean of this. So here I see a fraction numbers. That means wherever I have null, these values will return fractions. So this column also has fractional values. That means these columns contain some nans or nas. So let me capture these variables, I mean these features, columns, wherever I have null values, and I'm gonna do that by using a simple for loop here. I'm checking the condition. If the variable value is null and their sum is greater than 0, that means it will return fractional number, and that means these are the variables which contains null values. So let me print these variables which contains null values. So I see the output here. So these are the same columns which I see here as well, right? Now let me print the distribution, that is histograms, so that I can understand the characteristics of data. You know, whenever I get the data, plot the data. That will help you understand the insight and help you decide whether you want to use mean, median or mode. Okay, so the distributions that I see here shows some variance, right? So for this column I see some range, so it is between 0 to 120. So this histogram here shows me if I have to use mean, median or mode. Mode for sure we won't be using it for numerical values. If I see for lot frontage, I see data is skewed, it is not symmetrical data, lot of variations, so I might use median for this. And also for mass area, I see lot of values which contains 0 and high variance, highly skewed for other numbers, right? So I will definitely use median for this. And furthermore, also here for garage and for wood deck, for these columns also we should think of using median. Whereas for first floor, this column, I can think of using mean, right? We discussed it already, right? When to use mean and when to use median. Now all I need to do is capture the median of these three variables, three columns which we considered above. I'm gonna consider xtrain and variables to impute, basically the columns where we are gonna use imputation, and using simple median function here and converting it to a dictionary. So in return I'm getting a variables of dictionary for each type. So these are the median values for lot frontage, median value for mass 1 area, and garage, whatever the column is, this is the median value, right? Now we want to add these median values in the data set. How do I do that? To do that, I will replace missing data by simply using one function which is fill na. Xtrain fill na, and this is the dictionary where we have captured the median value which we want to replace, and I want to do it in the same data set. I don't want to create a new data set. So in place true stands for do it in the same place in the same data set. Okay, so let me execute that. Now let me quickly check, and if I'm getting sum as 0 and no fractional values, that means I do not have any nas or nans or missing data here. I can do the same for test data and see there are no missing values. Now if you want to impute mean, all you need to do is replace median with the mean function here. All the remaining code remains absolutely same, no change. Replace median with the mean, and that's it. Okay, now let me talk about quickly how do I handle imputation for categorical data, for characters, right? And for characters, you know that I'm gonna use mode. So these are the columns to consider, because I know that these are the columns where I have categorical data. Again, I'm loading the house price prediction, same data set here. Let me execute these columns. And if I print the head, you see that for this column, we have characters, right? Categorical data. So this is where I can think of using mode and not mean and median. Nothing different, same thing again. Let's separate training and testing data set. I'm dividing into 70-30 ratio. We are dropping sales price. We are considering only these two columns, because only for these two columns I want to identify mode. Let me execute this. So now I have train and test data set ready. I will just check if I have any nulls here and identify the mean of these. And when I look at the mean, I am getting a fractional values. I'm not getting 0. That means I have missing data in both the columns. Now all I need to do is capture the imputation values. Basically, what do you want to impute wherever you have missing values? So wherever I have missing values, I'm gonna use missing. So we have created imputation dictionary and I'm gonna embed missing wherever I have missing data. So this dictionary is ready. This is how it looks. Simply I'm gonna use fill_na function. Wherever you have missing values, impute this dictionary, meaning add missing variable in the same place. No need to create a new data set. Do it for train and do it for test. Let me execute, and now let me check the sum. If sum is 0, that means now I do not have any missing data. I do not have any missing values. Same goes for null and same goes for test. I'm just checking xtrain is null just to verify, do I have any null values? It will return boolean, so I see false, 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 everywhere false. This means I do not have any missing values in the dataset now. This is how we can impute mean, median and mode in my dataset. So this is very simple. We understood how to clean the data and perform the data imputation, different ways to perform the imputation. We encourage you to do more experiments with the feature engineering to see how it can improve the performance of your machine learning model. As we know, machines do not understand characters, that is categorical data. They do not understand characters, right? Then how do we work with categorical data, which should make sense to us and also to a machine so that it understands that characters and help us create the predictive model. As I've said, machines do not understand characters, that is categorical data. Then how do I convert that categorical data so machines can also understand and improve model's performance? This is called categorical encoding. So the process of converting categorical data into integer format. Machines understand numbers, they do not understand characters. And converting that categorical data to numbers is what categorical encoding stands for. In this video, we will deep dive and understand how to perform categorical encoding, and there are different types: one-hot encoding and ordinal encoding. And to know and understand how encoding impact on machine learning models, and most importantly, we are going to see the demo example, the hands-on on the same how to perform categorical encoding. First, let's understand different categorical encoding techniques and what their types are and what each type means here. So as you see in the diagram, we have mainly three types in categorical encoding. As you see, first one is the one-hot encoding. This is also called nominal encoding. Then the second type is ordinal or label encoding. And the third type that we have is count or frequency encoding. What does this each type means? When I say one-hot encoding, what it means? I'll just put the definition for now, and in the next slide you will understand what it actually means. So one-hot encoding is nothing but converting characters to a boolean variables. Converting character to 0 or 1, where idea is just to indicate if category is present for each observation or no, right? Character, convert it to 0 or 1s, binaries, and check if present or not. That is one-hot encoding, or also called nominal encoding. Then the second type, ordinal or label encoding, stands for where you put numbers but not only binaries, you put sequences 0 to n, that is 0, 1, 2, 3, 4 till n, where n is nothing but the distinct categories of the variables, and these numbers are assigned randomly. There is no sequencing as such, but we provide a number, a count, not only binaries 0 and 1s, right? Unlike one-hot encoding. And count and frequency encoding, where you put some logic as well, where each categories are replaced by the count or the percentage of observations that show that category in the dataset. Basically, if certain observations come multiple times, then we need a count, or we need to know the percentage full dataset, then we can use frequency, right? So these are the three different basic types that we have in categorical encoding. Let's understand with the example so that it will make more sense to you. So this is the image that I found on the Google, and definitely not created by me. I have also given the credits here, dailydoseofds.com. So why to waste time, right? So if something is very well explained and already created, so I have taken the reference of this image. If you see here, one-hot encoding, we converted these rows into columns, green, red, black, orange, right? And wherever that specific category is available, we are encoding 1, and if not available, then 0. So green is available here, 1, others 0. Same goes for red, 0, 1, 0, 0. Same goes for black, and same goes for orange. And there are some improvisations for one-hot encoding, which is also called K-1 or drop one feature encoding, right? Dummy encoding, which we are also going to see in the demo using pandas. Here, if you see drop one feature, that is K-1. K is number of features, right? 4 features. K-1 is 3. So we considered only 3 now. But if you observe,
it is not green, if it is not red, if it is not black, then definitely it is orange. So why do you need 4 columns, right? So that's why k minus 1. Then we have one more type, which is effect encoding, where let's say if none of the value represents any this color, then that's minus 1. Let's see one by one in detail. I'll jump to the next slide. So one hot encoding, as I've explained, I have data which something looks like this, number of 4 rows, and I have replaced it as columns. And you see wherever green is available, replace it with 1. If green is not available, replace that category to 0. Binary values. That is one hot encoding. Boolean values, right? 0, 1, 0, 0. For red, we have red available, but for other columns, red is not available. This is one hot encoding. Very simple to understand. Then as I've said, we have k minus 1, which is one drop feature encoding, right? We'll see that in the demo. Let's understand the other type, which is label encoding. A label encoding is nothing but where you provide a unique label, some random numbers. So I don't want 0 or 1s. I want numbers to each type. Let's say I want to represent green as 1, red as 2, black as 3. Right? So you see wherever we have green, we see number 1, red 2, black 3, and green again, it's not 4, it's 1, right? So we are representing each type with unique labels. So this is called label encoding. Very simple to understand. Then what is ordinal encoding? We also have something called ordinal encoding. What is ordinal encoding? Ordinal, name itself says order, data with certain orders. Here, these are not colors, but these are data with some orders, right? These are the sizes. So extra small is the first one, small second, then medium is third, and the large is fourth, right? So I want to number these values accordingly, which will make the sense as well. So extra small, you see 1, small 2, medium 3, and large 4. This is how we are encoding these values, and this is called ordinal encoding. Simple, easy. Yes, I know. Then what is count encoding? We have one more type of encoding, which is count encoding. Now I don't want the label, now I don't want the sequence or the order, but I want to count how many times this small came, how many times that green color came, right? So if you go to count encoding, you see that it represents the count of each type. So there is green, we see green 2 times, right? So in the encoding technique, it will put 2. Now these are not random numbers, these are not sequence, but it is count of each type, right? So green came 2 times, that's why I see encoding is happening based on the frequency. Then red 1, black 1. Okay, so out of 4 data sets, only for green feature we have 2. This is count encoding. Simple, right? I hope you understood the different types of encoding techniques which we have seen. So going back to this diagram again now, so that you can connect the dots and understand the different types of encoding techniques, right? One hot encoding, ordinal, and count or frequency encoding. So these are the 3 different types we understood. Now let's jump to the demo part and let's see how we can implement the same using Pandas and Jupyter Notebook. Let's come back to our original discussions. Okay, so this is the same demo which I have uploaded on the GitHub repository. You can find the link in the description below. Whatever implementations, demos I'm showing here, these are the same demos which are already uploaded to Git repository. So you can find that out in the description below and in the pinned comment as well. Okay, so we are on the feature engineering part, which is 0. I'll go to feature engineering and we already seen 3 demos, right? All of this you can ignore for now, and only one folder is important for us currently, which is data. This is where I have kept my data, house price and housing data, then Titanic. We are going to use Titanic dataset and housing price dataset for our demos. And here we are on part 4, which is categorical encoding. So I'll open this Jupyter Notebook. Okay, now let's see the demo. A one hot encoding using pandas. We are encoding into k-1 dummy variables. So it makes sense, right? I don't want to consider all the variables in one hot encoding, which we already discussed, right? I want to drop one feature, which is also called dummy encoding or k-1 encoding. K is number of features. So we have total 4 features, -1 is 3. So we are considering only 3 features here. Why 3 features? Why not 4? Because if it is not green, red and black, then it is definitely orange. So that's why dummy encoding, k-1 encoding. Let's see the same. I'm going to import pandas and model selection for splitting our data into train and test. So train, test, split. We did the import part. We're going to use only certain columns, and Titanic dataset I'm going to use here, right? So these are the columns I'm going to use. Let's read the CSV file which we kept here under data, Titanic dataset.csv, data.head. Let's execute. So this is how the data look like. So do you see that we have categorical data here, right? Machine understand 111 passenger class survived 110, right? But machine doesn't understand sex is female, male. So these are categorical. These are characters. It doesn't understand that. Similarly for cabin, you also have categories. For embark, embarked, we also have categories, right? So we need to replace these values with certain numbers. That is categorical encoding in simple words. And let's see how do we do that. Let me execute this cell as well. Here what we are doing is under cabin you see multiple strings, right? I just want the first letter and I'm printing it again. So you see cabin B, C, 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 right? So I removed unnecessary data and taking only the first letter here. Cool. Proceeding ahead, and very important in encoding, we need to split our data into training and testing, right? Though this is feature engineering, we should do that because these methods will learn patterns from the training data, and that's why we want to avoid leaking information and overfitting. So very important, divide our data into xtrain, xtest, ytrain, ytest. I don't want to consider the y column which is survived. Basically this is our predictor. In the Titanic dataset we know that, right? By looking at the data we need to identify if passenger survived or passenger didn't survive, right? But I don't want to consider that. That's why we removed this. This is our target, and test size is 0.3. That means testing data is 30% and training data is 70%. Random state 0, randomly select the sequence, and let's print the data how it looks like. So if you look at the shape of the xtrain and xtest, this is how the split looks like. 916 rows, 6 columns for training data, 393 rows and 6 columns for test data. Let's explore the cardinality to understand how many labels it has. So I'm looking for sex and using a unique function here which will show me how many different types we have under sex. So if you see under sex we have male and female. Very simple. Same for embarked, I'm gonna see the different types. In embarked we have 1, 2, 3, 4 types, also some question marks, right? And in cabin we have 8 labels and also missing data. So if you observe, it will also help you identify the missing data, right? So 8 types in the cabin. Why I'm doing this? Because this will help me know whether do you want to go for one hot encoding, whether you want to go for count or ordinal, what type of encoding you want to do. This is what you can decide by looking at the cardinality. So let's start with the basic one, that is one hot encoding. So once I understand the data, now I want to do the encoding for very first column, which is sex, right? And I'm gonna do that by using a very simple method in pandas, which is getDummies. So getDummies is a simple method which will help you convert your categorical data into binaries, and basically it is doing encoding for us. And let's see how it looks like. Do you see this? By simply pandas.getDummies and printing my temporary dataset, this is how it looks like. So this sex column above, if you see, this sex column is converted into the different cardinality features. So you see 2 different columns created, and wherever you have for passenger number 501, let's say if these passengers are female, you see 111, and this passenger is not female, so you see 0 here. So this is simple one hot encoding, 0 or 1. Very easy. We did a very simple method, getDummies. Now let's do the visualization better. Let's put it in the data set, and to do that I'm gonna do the concat in the original data set. So you see for column sex, concatenate this with whatever encoding that you did using getDummies, and let's print it by using .head. Okay, just in front of this you can see the concatenation happened, and now I can do the same thing for other columns like embark and also for the cabin. Very simple. Again, getDummies, I want to convert this categorical data into numbers, 0 or 1s. You see that this is happening for different types, and also I am gonna concatenate it for easy visualization. Let's do the same for cabin using getDummies, and it will convert those rows into features, and also it will do the encoding, converted those values into 0s and 1s. And I can also do this for all the variables together. getDummies will automatically recognize variable types, object and categorical type, ignoring numerical variables. So you don't have to actually do it manually one by one the way we did it, right? So manually I'm taking one feature at a time, one column at a time, okay? But we don't really need to do that. You can put getDummies for all the data, okay? It will automatically identify which features are of categorical type, and it will encode that. Okay, let's print and execute this. So you see 916 complete data set, and automatically it converted sex female and sex male into one hot encoding, and automatically encoding happened for sex female, sex male. For passenger class, if you see, it is already in numbers. It is not touching these variables, these columns, right? And if you see for cabins, again different features created. So getDummies is automatically taking care of encoding wherever there is categorical data. Okay, let's do the same for the test data set. And this is what I see, nothing different data set, right? So training, these many 916 rows, 18 columns and 393, and now I see only 16 columns. Why do you see a less number of columns for the test data set? This is because maybe there are chances that a type which we have chosen here, cabin A, B, C, the one of the type may not be available in the test data. So you see we have k-bin t type, which is available in train data, but this is not available in test data. So these are some of the limitations of get dummies. Doesn't really matter. Now let's do for k-1. As I've said, why do you want to consider all the features? I can do this for k-1. Alright, so here I just need to do drop first true. Nothing different. Same function, get dummies for which column? Sex column, drop first. Let's print this. Do you see this? Why do you need male and female two different columns? If I only have male, I can easily identify that means the passenger 501 is female, right? So for male it is 0. If male is 0, then the passenger number 501 is female. Yeah, so that's why k-1 or drop one feature encoding helps you reduce number of columns. It's a better way on top of one-hot encoding. Okay, same thing you can do for embarked. Rather than 4, now we have only 3. Same thing I can do for the training dataset. For complete dataset, I'm just doing get dummies for full data and drop first. This is k-1. Now if I'm doing k-1 for complete dataset, now this time I have 15 features. Without k-1, how many features I had on train dataset? Without k-1, I had 18. So do you see? Number of features are reduced. So that's why k-1 hot encoding is a better approach. This will reduce the information burden, right? And the processing power. Simple. Let's do the same for the test dataset. For complete test dataset, drop first true, pd.getDummies, nothing different. Let's execute this. Okay, for test dataset, we see 16 features without k-1, and when I do k-1 get dummies on the test data set, k-1 drop first, you see 13, right? So 2 features are reduced. Amazing. This is a very simple demo that we have seen to perform one hot encoding and one drop feature k-1 encoding. Hope you loved it. Alright, so in this video we have discussed feature engineering for machine learning, how to perform categorical encoding, and what are the different ways to categorical encoding and implement the same using pandas. We still encourage you to do some more experiments with the feature engineering to see how it can improve the performance of your machine learning model, right? So now let's talk about ordinal encoding, label encoding, and also the count encoding. Let's see the demo for these two types. Okay, what is ordinal encoding? Let's quickly recap. Ordinal encoding consists in replacing the categories by integers 1 to n or 0 to n. It's up to you. You have to decide, right? It's not only 0 and 1. In case of one-hot encoding, we wanted only 0 or 1. Available, not available. But here, I want to do the numbering from 1, 2, 3 to till n, right? So either you do it as a label or you do it as a sequence. This is what we need to decide. Here we're gonna use housing price dataset. Let's do the import pandas and model selection, train, test, split for splitting our data into test and train, read CSV, house price prediction, and these are the columns I'm gonna use. I don't want to consider all the columns. Look at this, and it also makes sense why I'm considering these columns, because these are the columns which are having categorical data. Okay, neighborhood, exterior 1, exterior 2. First of all, let's have a look at how many labels each variable has. So I'm gonna run for loop to see how many labels do we have. Let's print the numbers. So if you see, neighborhood has 25 labels, exterior 1 15, exterior 2 16, and sales price 663 labels. Okay, let's explore the unique categories under this. So neighborhood 25 labels, so these are the 25 unique labels. Rows are 663, total number of rows are 663, but unique values are this. I want 0 for this, 1 for this, 2 for this, 3 for this, so on and so, right? So I will have the count starting from 0 to 24 for neighborhood, or 1 to 25 for neighborhood, whereas total number of rows are 663. So this is what label encoding will help us to do. So let's see the unique categories for exterior 1 and also for exterior 2. So I have 15 labels, so these are the labels, and 16 labels for exterior, these are the labels. Okay, and again, not to forget, in encoding we should divide our data into xtrain xtest, ytrain ytest. Let's split the data. I don't want to consider the sales price. This is my predictor y column. Let's remove that. Test size is 30% and show me the shape of the data. 1022 training dataset, testing dataset 438, and we have 3 columns each. Cool. Let's perform the ordinal encoding now. And to perform this ordinal encoding, all I need to do is assign a number to each unique type. Ordinal encoding is what? I just want to assign a number, whether it can be random or sequential. This is what you need to decide. So this needs to be 1, 2, 3, right? That's what I'm doing here by using enumerate on neighborhood column for specific one column for now. Okay, and for unique dataset, start with 0. You can decide whether you want to start this count from 0 or 1. And let's see how does ordinal mapping looks like. So you see this, every unique category has assigned some number. Simple. All I need to do is map these numbers in the original dataset. Okay, let's do that. Xtrain neighborhood.map. This is the function I'm using. A map function will replace the categorical values with these values now. For that I'm using map. This is a dictionary. So map takes a dictionary, right? And same thing I can do for test. Let's execute this and let me print the head. You see this? And for neighborhood, now I have some labels, some numbers, and not the categorical values. So original dataset used to look like this. After label encoding, I see a numbers coming for each type. Beautiful. And these are not 0 and 1s. 0 and 1s, one hot encoding. This is label encoding. Okay, same thing we can do for exterior 1 and exterior 2. Same thing I can do for other two columns, right? And I'm writing a function, find category mapping enumerator for each type and doing the encoding, ordinal encoding here. Okay, let's create the functions for exterior 1 and exterior 2 and print those. Nothing different. So you see, we did the same for other two columns as well. So this is what a label encoding stands for. Isn't it cool? Isn't it easy? Okay, after label encoding or ordinal encoding, what is next? A count, right? If you remember from this diagram, one hot encoding we have seen already. Second is ordinal label, and third, count and frequency encoding. Let's see how do we perform count or frequency encoding now. So what is count or frequency encoding? Count and frequency encoding, we replace the categories by the count. I don't want random numbers. In one hot encoding, 0 and 1s. In ordinal or label encoding, we had random numbers or the labels, but now I want the count for each type or a frequency. Count we can easily understand how many times that observation is coming, right? So that's the count. But frequency is nothing but you want a percentage of observation in the dataset. So for example, let's say 10 rows out of 100 are of color blue. Then I want a percentage, right? Then what is the percentage of color blue? That is 0.1. That is 10%, right? Which we represent by using 0.1. This is called frequency encoding. I am printing the percentage of that specific dataset. Blue colors are 10 out of 100. So percentage or a frequency is 0.1. That's what frequency encoding is. This might also be needed when you do the encoding in categorical data. Let's perform the same. Nothing different again. I'm gonna import the pandas and train, test and split. Read the CSV houseprice.csv, read the dataset houseprice.csv. These are the columns I'm considering. Let's print the head. We did this multiple times now already, right? Now if you see, I have categorical data. I don't want to perform label encoding now, right? I want a count or frequency. Let's see the unique labels for each data type. I'm printing the labels for each type. Neighborhood 25 labels, exterior 15, exterior 2 16, cells 663. So number of unique variables we printed here. Then again, as we have seen before, split our data into test and train, 30% test size, and consider only these columns and show me the shape of train and test. 1022 rows, 3 columns, 438 rows and 3 columns for test. How do I perform count? You just need to use a function. I'm using a very simple function called count. We know that map is a function that we use. Important here is to understand a map is a simple function which takes a dictionary. So you decide what dictionary you want to create. Do you want to create a dictionary of labels or random numbers, or do you want to create a dictionary of counts? So this time, unlike label encoding, I'm creating a dictionary of count. So for neighborhood column, I'm using values.count and converting it into dictionaries. It will give me a count. So you see names, 151 names. So I got a count for each type. For each unique type, I have got the count. So blue, whatever, blue tea, I have 2. So I got the count for each type. Now I can map this to my original dataset by using map function, xtrain neighborhood map and the dictionary. This dictionary you can create as per your need, whether a count or a simple sequence of numbers. Label encoding, right? It's up to you. Execute this and let's print the head. Now do you see I have the count encoded here. Similarly, I can also do the frequency encoding. What I'm doing here. So in frequency encoding, all I need percentage. So what do I need to do? I need to divide the count by total number of observations. Okay, I need a percentage. That's why I'm dividing the count by total number of observations, right? So values count will give me a count, and I'm using a simple parameter here, normalize is equal to true. This will give me a frequency and not the count. Okay, so I have a dictionary ready. Do you see? So 151 type, this is the frequency, 14%, 14.77, right? 105 is 10%. I got a percentage of each type, and let's map this in the original data set. So I'm gonna use xtrain map frequency and let's print the head. Beautiful. So neighborhood is now encoded with the frequency now. Okay, this is frequency encoding, which is percentage of each type, or you can do the count encoding. This is how the count and frequency encoding can be done. Very easy to understand, right? Important is map function and the dictionary that you need to prepare.
Feature transformation is a crucial step in the machine learning pipeline where we manipulate or modify our data features to improve the performance of our models. Feature transformation is a crucial step in machine learning pipeline where we manipulate or modify our data features to improve the performance of our models. This video we will deep dive and understand what is feature transformation, why and when to use feature transformation, different transformation techniques such as function, power and quantile, etc. Understand their impact on the machine learning models, and for sure we are gonna implement them using scikit-learn and Jupyter Notebook. In the machine learning pipeline, after we get the raw data, 70% of the time is spent on data cleaning and preparations. And why do we do that? So that we can provide a quality data to the machine learning model, and hence we can have a better predictions. Quality of the data is directly proportional to the accuracy of the model. So a feature transformation is a technique by which we can boost our model's performance. If I want to define formally what is feature transformation, a transformation in which we apply a mathematical formula to a particular column, that is feature, and transform these values which are useful for our further analysis, and in turn we get better model performance. So in the machine learning pipeline, as you see in the image, a data preparation is what we are talking about. We already discussed about data processing and data cleaning. Now we are talking about the second part under data preparation, which is feature extraction. And after that, we are gonna see a feature scaling and the selection in future videos, right? So once we have a data prepared, we provide it to our model, to our machine learning model, so that it can give a better accuracy. And then we evaluate. If the predictions are not up to the mark, then we retrain, reiterate and improve the accuracy of the model, right? This is what we keep doing. Then we finally deploy and monitor our predictions. But the question here is how feature transformation increases the performance of our machine learning algorithm. The answer is distribution of the data, which is not normally distributed, which has very large impact on the linear models like linear regression, logistic regression. So feature transformation is a technique where we use mathematical formulas to normalize these distributions, and hence it boosts the performance of our machine learning algorithms, right? Let me give you an example. I know that this is difficult to understand. What is distributed data? If you see here in the image, the data is called skeeved, right? So this data here which you see is positively skeeved, or data can also be negatively skeeved. But the data which we require need to be Gaussian for most of the algorithms, linear regression and logistic regression. If your data is normally distributed, this is normally distributed data, which is Gaussian data, and this is skeeved data, this is unbiased data, highly skeeved data, positive or negative, doesn't matter, but data is not normally distributed. So this is one of the example. Also, as you can see in the image, sometimes the data may not be linearly separable, right? So as you can see on the left hand side, we have a data in this format. This is not linearly separable. I cannot draw a line to separate green and red. So what is the other way? So something which cannot be solved in one dimension. So this is two-dimensional data. Can I transform this data into other dimensions? Maybe in 3 dimensions, right? So if I transform that data into other dimensions and look at the data from other angles, then there are chances that data can be linearly separable. And this is where feature transformation with kernels comes into a picture. And we discussed very nice example during SVM, right? So SVM support vector machine sometimes may have a data which is not linearly separable. So we use kernels there, and these kernels will help us transform the data and make the data linearly separable by transforming that data into other dimensions. So just to show you the outcome of how the data will look like if I don't use the feature transformation, and after applying feature transformation, what is the outcome? Let me show you that. If you see here, this is data distribution which is plotted, right? So if you see here, this is before applying transformation. As you see, data is positively skeeved, isn't it? Data is not normalized. And if I plot a QQ plot, this is how the data will look like. So data is in the blue color, and the line that we see here is in the 45 degrees. And this is a linear line which will act as a reference to the actual data. I can see data is linear, but it is not that linear.
So for linear algorithms, linear regression, logistic regression, I can provide this data, but is there a way by which I can still improve the performance of our model? So if I apply the transformation, this is how the data will look like. So data is Gaussian now, data is distributed normally. You can see the difference between this before and after. And when I plot a QQ plot, this is how the data look like. You can easily see the difference here, right? So data used to look curved. Now data is very much linear. And when data is linear, I have better accuracy in linear algorithms. And hence, whenever you get the data, it is always better to plot the data to check if the data is positively skeeved or if data is negatively skeeved. Positive or negative is nothing but data is biased, right? And what we want is symmetrical distribution of the data, something like this, where mean, median, mode generally comes at the one line, isn't it? This is what we are aiming for. So if this is very much clear to you, what is feature transformation? Let me talk about what are the different types of transformation and what are the different techniques by which I can make the data symmetric and normally distributed. So you can see in the image, we have something called as log transformation, we have reciprocal transformation, we have square transformations, square root transformation, power transformation, and also we can have a custom transformations. We'll talk about these in detail, but in a minute. But before that, let me tell you why and where should we use these feature transformation techniques, so that we should be very clear when to use and when not to use, right? So first of all, linear and logistic regression. So in linear and in logistic regression, some data science models assume that variables follow the normal distribution, but this may not be true. The raw data which we get, we don't know the nature of the data. So that's why I always suggest you to plot the data, understand the nature of the data. And hence, these transformations are generally used where data is linear in nature and not on decision trees or on the random forest kind of algorithms. And we know that most of the time variables in real dataset will follow skeeved distribution or biased data. And hence, by applying these transformations to these skeeved variables, we can map these skeeved distributions to the normal distributions so that we can increase the performance of our model. I hope why and where part of feature transformation is very much clear to you now. Now let's talk about what are the different types of transformations. So basically there are three types of transformations. First one is function transformer, second one is power transformer, and the third one is quantile transformer. So talking about the function transformer, there are three more subtypes if you see, and these are very much popular, right? So function transformer and power transformer are the ones which are generally used. And in function transformer, we have log transform, we have reciprocal transform, we have square transform. Don't worry about what are these different types of transform and when to use. I'm going to talk about that. But for now, let's just understand the different types, right? So under the power transformation, we have two different main types of transformers. First one is Box-Cox transform, and the second one, which is very much popular, is Joule-Johnson transform. Let's quickly talk about each one of these different types of transforms so that you understand and you decide when to use which transform. Talking about the very first function transform is a log transformer. What is this log transform? We apply log to every value of that particular column to make their distribution normal. So basically we are applying just a log to every value so that they become normal, and hence eventually this will give us the better performance of machine learning algorithm. Where to use? When you see a particular column has only positive values, because we know that log cannot take negative values. So it is used only for the positive values when data is positively skeeved. And how does it work? Sometimes you see that columns has large scale than other columns. So you may see there is a huge difference between the scale of different columns, right? For example, in one column, let's say I have an age of a person, which is in numbers. Let's say 25, 26, 30 is the age. These are the numbers, positive numbers. And the other column shows weight of the person. But the weight of the person is in milligrams or even in grams. So the value in the grams or in the milligrams will be very large. 60 kilogram person is actually showing 60,000 grams, right? Value of the weight are given in the grams and age are given in numbers. Age of the person, let's say 25, and weight of the person is, let's say, 60,000 grams. You see a scaling problem here, and this is where a log transform can be applied. And what will happen because of this? It will help you put the data into the certain range, normalize the data. right? This is where log transformers can be used. So you can see in the image, before applying log transform, data is positively skewed, right? And you can see the QQ plot here. This QQ plot suggests the data is not linear, isn't it? So can I apply log transform here? So after applying log transform, I can easily see data is very much linear now. Data used to be curved or not scaled or not even distributed. Now it become linear. So definitely after transformation, the predictions which I'm gonna get will be more better for linear algorithms, isn't it? Okay, what is reciprocal transform, which is second type under function transform? This is useful when we have ratios. When we have positive numbers, we use log transform, but when we have ratios, we use reciprocal transform. Very simple. Basically division of two variables, right? So when should we use? If you have again a skeeved data which is heavily skeeved, having long tail of large values, so taking reciprocal of that can help normalize the distribution. Sometimes you also see the problem with the proportional relationships. Let's say we have two columns where one column is working hours and the second column is, let's say, family time. So if working hours increases, then definitely the time for family will be decreased. So this is what inversely proportional data. So when working hour increases, time to family decreases. So this is where you see a proportional relationship between the features. So whenever you see inversely proportional data, so because of this, biasness and skewing is natural to the data. And this is where we need a normal distribution. Then reciprocal transform can also be used to stabilize the variance. Particularly if variance increases, the feature value will also increase. So reciprocal transform will be helpful. The model which will assume the constant variance, right? Such as linear regression. We don't want higher variance. We need the stable variance. So that's why we can think of using reciprocal transform when we want to stabilize the variance. Importantly, when not to use the reciprocal transform. So reciprocal transform is not suitable for all type of data or in all situations, generally used for linear models. Apply this when you understand the underlying data characteristics, because there can be a potential issues that may arise. If your data has a division by 0 or close to 0 values, this can impact the effectiveness of the reciprocal transform. So make sure you understand the data first. Then only apply the reciprocal transform, because reciprocal transform is a ratio based transform. Okay, and here in the image you can see result of applying reciprocal transform. These are the QQ plots which you can see. This is before applying transform, right? Data is very non-linear. This is curve. I should make data linear, right? So when I apply this reciprocal transform, when data is ratio based and make sure data is not divisible by 0, then I can apply reciprocal transform. So once I apply that, data looks very much linear. You can easily see the difference between these two QQ plots here. In the next video, we are going to see the demo for the same, so that you can also apply, try yourself and see the results for yourself. Then there is a third type of transform under function transform, which is a square transform. So the name itself says, right, the square transform which computes the square of each feature value. So it just squares the value. Let's say if the feature value is x, then it converts that x into x raised to 2. It's just a square. So when should we use square transform? For non-linear relationships. If you see, there is a non-linear relationship between a feature and the target variable, that is y column. Applying these square transform can help capture the relationship. It can enable a linear model to better fit the data, as it can model curved or quadratic patterns, right? So square transform is the best fit when you see a non-linear relationship between two different features. Or you see the scaling differences when there is a significant differences in the scale or magnitude of the features. And you know what? Sometimes squaring the values can help you balance out these differences and bring them to more comparable range. That is, it will help you normalize the data. And finally, square transform can also be used to stabilize the variance. So if the variance of the feature increases as the value increases, applying square transform can help stabilize the variance. Okay, how does square transform work? The squared values introduce non-linearity into the relationship between the features and the target variables. This allows for modeling more complex patterns and capturing curved relationships that a linear model might struggle to represent. So square transform introduce non-linearity into the relationship between the feature and the target variable. This is how it works. or it does the magnitude amplification. Square transform amplifies the difference between the smaller values while compressing the difference between the larger values. So it boosts the smaller values and compress the larger values. This will help normalize the data, and this is what we want. And importantly, it will have a huge impact on the outliers. The square transform can magnify the impact of outliers, as squaring extremely large or small values can result in even larger values. This effect should be taken into consideration and handled appropriately. So make sure you consider the outliers if they have extremely large or extremely smaller values. And hence, square transform cannot be the best fit if you have more outliers with bigger or the extreme smaller values. And again, this is where you see after applying the square transform. So before applying square transform, you see data is very much linear, right? This is a QQ plot. And after applying a square transform, you can see data is very much linear. So definitely after applying square transform on these type of data, the predictions will be more better. You can also observe the outliers here. So number of outliers are lesser here, but after applying square transform, the outliers value gets magnified, and that's why you see magnified values of the outliers here. Amazing, right? Definitely we'll see the demo again in the next video. Okay, so now we know all the function transforms. So we have seen log, reciprocal and square transform, what they are and when to use, right? And also how they work. Now let's talk about what are power transformers. These are really very easy to understand. Let me talk about these. So when do we use power transformers? Power transformers is used when the desired output is more Gaussian based, when we need more normal, distributed or proportionate output. And there are two types of power transformers that we have. The first type under power transformer is a Box-Cox transform, and the second one, which is more popular, which is Johansson transform. So when should we use Box-Cox? Box-Cox transform should be used when input data is strictly positive. This will not even accept zeros. Okay, so if you have positive data, then it is better to go for Box-Cox transform. And hence we have come up with the new idea or a new transform, which is Johansson transform. And I generally call this as an enhancement over Box-Cox transform. And if you have zeros or negative values in the data, Johansson transform comes to the rescue. So in this video, we have discussed feature engineering for machine learning and specifically the feature transformation techniques. When we are working with the linear model, it is necessary to normalize the scale of the data for the better performance. The feature transformation technique has a lot of variants available to do the task of normalizing the distribution. But at the end of the day, it totally depends on us what approach will best fit depending on the nature of the data.
Now we're gonna talk about feature transformation using sklearn. Okay, let's open this one. Okay, so here in this video we are performing function transformations and the power transformations, and the dataset that we are using is California housing dataset. These are the characteristics of dataset that you can see. The attribute information is already given here. Mid-INC stands for medium income in the society, house age, average rooms, average bedrooms, population. We are very much aware about this dataset already, right? And we're importing this dataset from sklearn dataset itself. Okay, so let's perform the first transformation, logarithmic transformation. First thing first, not to forget, import the libraries. I'm gonna use NumPy for statistics, Pandas for data frame, Matplotlib for plotting, and SciPy for scientific plots, which is QQ plot, right? And the dataset that I'm using is from sklearn California housing dataset, right? I'm using it directly from the sklearn. And importantly, not to forget the function transformer. This is why we are here, right? And again, we are importing it from sklearn, pre-processing, function transformer. This is the library we are using. After this, we are loading California housing dataset in X and Y, X input, Y output, right? And let's print the dataset here. After execution, and let's display the first 5 rows here. You can see this is how the data looks like. So just by looking at this data in the numbers, it is very difficult for humans to understand if data is distributed, if data is skeeved, not skeeved, very difficult, right? So that's why we take help of plot. Thumb of a rule is whenever you get the data, plot the data, isn't it? That's why I'm gonna use the histograms and QQ plots to understand the nature of the data. And we will be plotting it again and again for all different types of transformation. That's why we have created the function here, which takes data frame and the variable for which you want to draw the histogram and the QQ plot. Here you see we are using Matplotlib and drawing the subplots, and on the data frame, this hist function will create a histogram for us. And same for the QQ plot here. We are using stats probability plot here, defining for which variable we want to draw the QQ plot, and finally using matplotlib so that we can draw the QQ plot. This is it. For now, let's try using this function and see the nature of the data without using transformations. So I have called this function by passing the raw data which we received here when we imported our data, and the variable which I want to consider is median income in the society. And when I draw the plot, this is how it looks like. Do you see this? The histogram shows the data is not Gaussian. Data is positively skewed, right? It doesn't look like a bell curve. And similarly in the QQ plot, I can see data is not much linear, it is curved, and hence it's gonna affect the accuracy of the model if I use these data as it is. Okay, so I have to make sure data is unbiased, data is Gaussian, and I have to make data normalized, and that's why I'm gonna use the very first transformation, which is logarithmic transformation. Let's consider the variables for which I want to use the logarithmic transformation. These are the variables on which I'm gonna perform logarithmic transformation. Now before I perform any operations, let me take the copy of input values, that is X copy. I'm creating just the copy of the values so that the original data set doesn't get affected, and this is the most important step that we need to perform. We did the import and we are gonna initialize the function transformer and pass the required parameters here. What transformer we are using here? A logarithmic transformer, right? So that's why function is equal to np.log. NumPy provides us different mathematical operations to perform, right? So np.log I'm using, this is the function I'm using here, and I'm also performing inverse of these values by using np.exponential just to convert the variables into its original form. Okay, this is the variable where we have initiated. Now I'm going to use a very simple function here which is called transform on the variable transformer and pass for which variables you want to perform this log transformation, and in return I'm gonna get the variables which are transformed as mentioned. And now next thing is, let's plot it and see how does the data look like now. Again, diagnostic plot, right? So for the diagnostic plot, the new transformed variables, and for which variable, which exact column, right? This is the column we have seen. So just to remind you quickly, let me show you before performing transformation, this is how it used to look like. Look at the data, this is positively skewed. Look at the distribution and look at the QQ plot here. Data looked little curved, right? It is not in line with this 45-degree line here. And after performing transformation, let's see the output here. What do you see? Amazing, right? Data is very much Gaussian, normalized, and in line with the 45-degree. Okay, so see here again. So this is before, this is after. Simple, great, right? This is the power of transformation. All right, if I want to inverse this or get the original values, then I'm gonna do the inverse transform on the variables and again do the plotting, right? So you see this is before, this is after, right? Same thing. So let's assume if your variable contains 0 or negative numbers, then how do you perform logarithmic transformation? It's very much important. If you know, logarithmic transformation can only be performed on the positive numbers, right? So if your data contains zeros or negatives, then I need to add the constant. And let's see how do I do that. If I have negative values or zeros, then I'm gonna use the lambda function here. Okay, same thing, take the copy, use the function transformer, and in the parameters what I'm gonna pass is np.log plus 1. So this is the constant value that I have added, x plus 1. For each variable, lambda is used. It's like an inline for loop, right? So I have used lambda function to add constant for each variable, which is 1. All right, so I have initialized the transformer, and now I'm going to use the function called transform and get the new transformed variable list. And let's plot this using the function diagnostic plot, which we initialized here at the start, right here, which eventually draws histogram and the QQ plot. Okay, so the output here is not much different because we just added a constant plus 1 here, right? So that's why the output is very much similar, right? We didn't really require to add the constant plus 1 here, but just to show you the demo, how do you work with negative values and how will you add the constant if logarithmic transformation you ever use. Okay, let's proceed for the next one, the reciprocal transformation with sci-kit learn now. Here we are using column called average occupation. It's nothing but average number of members in the house. Okay, and we are plotting the histogram and the QQ plot for the same, just to check how it looks before and after. It is not at all distributed. Data is highly biased. Okay, it is not normalized data in any way. Okay, so let's perform reciprocal transformation on this. I'm gonna use the same function, which is function transform, but only difference that you see is this. Rather than np.log, I'm using np numpy.reciprocal. This is the only change I'm gonna do, right? Rest of the things remain same. Transformer.transform, pass the column for which you want to perform the transform. This is the transform variable. Now let's plot the new transform feature here, which is average occupation. So if I execute this, you see at least data distribution is improved to some extent, right? This is after performing reciprocal transformation, and before performing transformation, this is how the data used to look like. Not distributed at all, very bad. And here at least I see some linearity, or at least some distributed data after performing transformation. Definitely after transformation, this machine learning model will definitely provide me more better accuracy and the performance, right? Hope you understand how we are performing transformations. What we are doing here are the very simple steps, right? Import the library function transformer, initialize the function transformer, pass which type of transformer you want to use, log, reciprocal, or square root, or power transformer, and then use one function which is nothing but transform, and the new data, new column will be completely transformed for us. And finally, we are plotting QQ plots just to see how data looks like before and after the transformation. Okay, so if you are good till here, let's proceed and talk about the next transformation, which is square root transformation. For the square root transformation, we have created the data set, data frame here of count 1 and count 2 of this size, right? So we have two columns and these many rows here. You can see the data here. We have printed the data. We have displayed the top 5 rows here. Then I have taken the copy of the data frame and performing the function transformation. Nothing different. It's absolutely same. The name of the transformation itself is square root transform. This means I'm gonna take a square root of each feature here, and the same thing we are doing here using lambda function, so that I can apply square root on each row, on each value, np.square root on each data set, and round it till 2. I round the value till 2 decimals by using np.round and using lambda to perform on each and every value that we are going to pass in the data set. Okay, let's execute. And here using the transform function, passing the data frame count 1 and count 2 on which I want to apply this square root transform, and let's print the data to see how does the transformation looks like. This is how the transformation looks like after performing square root transformation. Don't worry about the plot here. We didn't perform this transformation on the housing data set. We created our own values here just to keep the simplicity. Important thing to understand is how did we apply square root transform here. This is the simple function that we have used. Talking about the most important transformation that I use generally are power transformations. Let's see how we're going to perform power transformation. We're going to see the demo for Box-Cox transform and Johansson transform. We have seen the demo for these 3 types already, right? So let's see how it goes. Coming back to Jupyter Notebook, I'm using these 2 variables, average income and the population. These are the variables on which I want to perform the transformation, taking the copy of the data set, and importantly, nothing different, using function transformer library here. As name says, power transformer, that means np numpy.power. In this case, we want to power every variable with 0.3. It is user defined. You define what is the power that is required for each variable, right? So we want to apply power for each variable. That's why we used lambda function here, and this is how we initialized our function transformer to perform power transformation. And nothing different, using transformer.transform function on the input variables which I have initialized here. And finally, I'm gonna get the data frame of transformed variables. Let's see how it looks like by plotting the data using diagnostic plot for median income column, and also we plotted it for population. So this is the output that you see after performing power transformation. Do you see the transformation? The data is very much Gaussian and normalized, and also in the QQ plot I can see data is very much in line with the 45-degree line here. And if you remember, this is the same variable we used at the start of this demo, right? And before performing transformation, how it used to look like, let me scroll a bit above and show you. See, for median income column, this is how it used to look like. QQ plot is curved, data is not distributed. This is before, and this is after performing QQ transformation, where it's gone. Yeah, this is where you see. And you see a huge improvement in the normalization. That's the power of data transformation. Okay, last but not the least, let's see what is Box-Cox transformation. Okay, so that's the power of using user defined transformation, nothing but the power transformation. Now let's see the very specific transformations which are really used in the real life, nothing but Box-Cox transformation and the Johansson transformation. Okay, let's see them, how it looks like. Alright, for the Box-Cox transformation, we are considering only the specific columns here, dropping latitude and longitude. Okay, and let me print the initial 5 rows and plot the histogram for all the considered columns. Okay, we just dropped these 2 columns, latitude, longitude, just to reduce the number of plots here. Okay, so we can see 6 histogram plotted here for the 6 columns, right? So you can see here, this is before performing transformation, not so Gaussian, positively skewed. This one looks like a normal distribution, very bad distribution, very bad, very bad, very bad for all other columns, right? Let's see after performing transformation, how does these variables look like. Let's convert the variables in the form of list so that it becomes easier for me to draw the QQ plot again. So we are just drawing the QQ plot here by using probability plot and show the QQ plot. Okay, so if you see, QQ plot looks something like this, right? Data is not so linear, not in the 45 degrees, not so linear again, not so linear again, not so linear again, right? By looking at this, I can easily understand only for house age, data is unbiased and Gaussian, but for other columns, it is not. So let's perform the transformation to see before and after performing transformation. So again here, I'm using the same thing, which is power transformer. What is the method that you are using? And trust me, these are more easier now. So I just want to define the variable, method, and provide what type of transformation you're going to use here, and use the function called setOutput so that you can convert the transform into the pandas data frame. Once the initialization is done, rather than using transform function, we are using fit function here. You see, we are not using transform, we are using fit function. So in short, the initialized transformer will learn from the lambdas that you have provided. Okay, learn from the lambdas that you have provided here. So I'm using transformer.fit and all the input variables which we have defined initially. If you want to see the lambdas, it's very simple. Transformer.lambdas, you can see something like this. So this is the array of lambda that you see here. And finally, use transform function to transform our raw data to the Box-Cox transformation. Transformer.transform, the function transform and the input value, and I'm catching it in new variable. Let's print the dataset, how it looks like. The new transformed variables, the lambdas you can see here in the table. And finally, without plotting these columns, I don't understand. So that's why let's plot the histogram and see how it looks like. Do you see, after the transformation, the output is much better, isn't it? You see, this is after performing Box-Cox transformation, right? Look at these graphs. Data looks Gaussian, unbiased, right? Normalized. And if you see here, before performing transformation, this is how it used to look like. Okay, you can just pause the video and compare these two graphs, right? And let's plot the QQ plot to see how it looks like. Great, do you see a 45 degree and the data is in line with this red line? So this is after performing Box-Cox transformation, and this is before performing Box-Cox transformation. Pause the video and yourself compare these plots, right? Before and after. Great. Now last but not the least, which is Johansson transformation. Again, the most popular transformation out of all transformation, I would say. How we gonna use? It's very simple. Again, power transformation, again power transformer library, and only one thing that we need to mention here, rather than Box-Cox, the method is Johansson transform. We did the initialization, set the output to pandas so that I can get the data in the pandas data frame. After initialization, not to forget to use transformer.fit the raw data. Now this will help learn the lambdas, meaning this transformer will be applied on every variable, and you can see the lambdas here by using the variable called lambda. You can print the lambdas by using transformer.lambdas variable. This will give us the array, and after this, let's use the transform function, which will actually help me perform transformation from the non-Gaussian data, positively skewed data, to Johansson transformation. And let's print the data set here. This is how the data set look like. And not to forget, let's see the output by using matplotlib, histogram, and the QQ plot. Definitely you can see after performing Johansson transformation, the output is much better, meaning data is very much Gaussian, data is very much inline, distributed, unbiased, right? So eventually it will help boost the performance of our model. Let's talk about feature scaling. What is feature scaling? This is the secret to supercharge your machine learning model. The scaling of the features ensures that a feature with a relatively higher magnitude will not control the trained model. I know you didn't understood anything, right? Let me give you a simple example here. Imagine your house has a one tiny bedroom and a gigantic living room. Would you sleep comfortably? Probably not. Scale or the magnitude of the rooms are not really matching. So machine learning models face the same problem when features have widely different scales. That's where feature scaling comes to the rescue. Because this video, which is feature scaling, is done towards the end of data pre-processing and just before giving input to the models. So in this video, let's deep dive and understand what is feature scaling, why feature scaling is so important, what are the different feature scaling techniques such as normalization, standardization, and many more. Understand their impact on the machine learning model, and definitely we are going to implement them using scikit-learn and the Jupyter Notebook. First thing first, let's talk about the need. Why feature scaling? Look at this picture. This picture explains everything. The gigantic sumo on the left hand side competing with the kids on the right hand side. Look at the magnitude in the strength. So we have two categories here, features with the higher magnitudes and the features with the lower magnitudes. Let me show you one more image here. Look at this image. The image of apple and strawberry. The size of the apple is relatively bigger than the size of the strawberry. So the upper part of the image is unscaled data. If I perform the scaling, you can see size of the apple and the size of the strawberry remains same without losing its intrinsic value, that is test, and its actual characteristics, right? That is what scaling stands for. Let me give you more technical example. Look at the dataset here, which includes two key features: size of the house, which is in square feet, and number of bedrooms. If you observe, size of the house is given in the square feet, which is 800, 1200, 1500 square feet, and in the other column, the number of bedrooms is given, which is 1, 3, 2, 4. And what do you observe? The difference in the range is vast between two numerical features. To ensure that all features are given equal importance, we need to scale so that reasonable importance is given to the minor features as well, which is number of beds in this scenario. Why we are discussing this? Definitely variables with a bigger magnitude or the value dominate over the smaller magnitude or the value. And to prevent the machine learning algorithm from unbiased functioning, this is why we need feature scaling technique. But the question is, does all machine learning models gets affected because of unscaled data? Let me show you that. So generally speaking, the machine learning models where distance is measured and distance is the major criteria to calculate the accuracy of the machine learning model, then feature scaling is really important. Like linear regression, logistic regression, where distance is measured between data points and the line drawn, right? Similarly, even in neural networks, in support vector machines, in KNN, in K-means clustering, linear discriminant analysis, or PCA, which is principal component analysis. In all these algorithms, we calculate distances. And you know what? The coefficients gets affected by the magnitude of the features. This is why feature scaling is really important. We don't want to draw a line which gets leaned towards the higher magnitude values, right? We need unbiased predictions. And where does feature scaling is not required? The machine learning models which are based on trees like classification, regression trees, random forest, gradient boosted trees. These algorithms are generally based on numerical calculations, and hence feature scaling is not required here. And that's why we need feature scaling in feature engineering pipeline for these reasons, which is nothing but to ensure uniformity and the balance between the features. It also facilitates better convergence during the model training. It allows the algorithm to take better predictions. It also helps boost the model's performance and the efficiency of machine learning algorithms, especially where gradient descent is used. Alright, I hope this helps you understand why feature scaling. So now let's understand how do I perform and what exactly feature scaling is. Feature scaling refers to the method used to normalize the range of values of independent variables. In other words, the method to set the feature value range within the similar scale between 0 to 1 or -10 to +10, whichever scale you think is the best fit for the data. In between that range, you try to fit values of that column. But you know, feature scaling is generally the last step in the data pre-processing pipeline, performed just before training the machine learning algorithm. As you can see in the image, this is just performed before you pass the data to our actual model, right? Okay, but how do I achieve this? What are the different techniques to achieve feature scaling? So the most popular feature scaling methods are called normalization and the standardization. As you can see in the image, this is the actual data which is unscaled. drawn against x and y, you can see after normalization, data is in between 0 and 1. You have the scale in between 0 and 1 on x-axis and also on the y-axis. This is normalization. And in case of standardization, data is mean centered. And again, the data to achieve a range of 0 to 1. But how do we calculate the range? It cannot be only positive, it can also be negative by calculating mean and the standard deviation. How does it work? Don't worry about it. We are gonna see the demo for the same. But you know, the important question is, does scaling have any effect on the intrinsic value of the features? Actually not. So feature scaling does not change the shape of the distribution. On left hand side, you can see the distribution. This is original scale, and the distribution plot is drawn for the house price prediction dataset. You can see the data distribution before performing standardization and after performing standardization. Looks same here, 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 and also here, house age. So distribution doesn't really change. So what really changes? If you observe, the data is mean centered now. The starting point for this column is 0, 0. If you see for here, it is 0 and -2 as well. If you see after standardization, the center is moved, right? Same for house age, right? 0, 1, 2, 0, -1, -2. But here, this is something different. Observe for latitude and longitude, 32.5, 35. But after standardization, data is range between 0, 1, 2, 0, -1, -2, right? So the data is mean centered now in between some specific range without losing its intrinsic value, meaning without losing its distribution. Even if I perform this on min-max scaler, which is one of the technique in normalization, you can see here, again, the distribution doesn't really change even in case of mean-max scaling, right? So you can see here, the data is between 0 to 15, and here data is drawn from 0 to 1, 0 to 1, 0 to 1, 0 to 1 for all the features, 0 to 1, even for latitude and longitude. Does that mean the shape of the distribution is changed? It is not. The intrinsic value should remain same. The plot should remain same. The benefit that I'm gonna get is unbiased magnitude and better performance and the efficiency to calculate the distances, and eventually machine learning model will be more efficient if you perform the scaling techniques, if you have already performed scaling on the data sets. And some of you might ask, what if I want to change the distribution? To change the distribution, there is a different technique which we discussed in the previous video, which is feature transformation. To change the distribution of the data, we use feature transformation technique, a logarithmic transformation, reciprocal, square root, Box-Cox, Yeo-Johnson. So these are the different techniques we have already seen in the previous videos. If you have not watched, please go and see how do we convert our SCIF data to the Gaussian data. Alright, just to show you the result of performing feature scaling, I have executed this demo. We are going to see this demo in detail in the next video, but for now, just to understand what will be the result after performing scaling. That's why I'm showing you this output directly here. We have considered two features here and we have drawn a scatter plot, right? Don't worry about what data, which data is considered. So this is without scaling. The green scatter plot which you see is without scaling, right? When data is drawn without scaling, you can see data ranges between 10 to 15 without scaling. And also for y-axis, it is in between 1 to 6, right? So if I have performed standardization, which is in the pink color, you see data become mean centric, right? 0 to 2.5, 0 to 2.5, 0 to 3 on y-axis, and 0 to -2 on negative y-axis. This is mean centric data. And what happened with the normalization? When I performed min-max scaling on this data, you can see data is only here. The data range is converted only between 0 and 1. Okay, it is not more than 1 here, even on the x-axis and also on the y-axis. So the data which is drawn here and here is absolutely same. The distribution will be absolutely same. The only difference is the scaling, the magnitude. We are keeping the magnitude same. And this is the benefit of performing feature scaling. Alright, in this video, we have discussed feature scaling for machine learning, why and what is feature scaling and its importance. In the next video, definitely we're going to talk about techniques to perform the same and how do we do the normalization and the standardization. So what exactly standardization stands for? Before I jump for the demo, let's understand what standardization stands for. Standardization is your go-to for many algorithms. It transforms your data so it has mean of 0 and a standard deviation of 1. In short, it centers the variable at 0 and sets the variance to 1. In simple words, it pictures your features neatly packed within that bell curve. This helps with distance-based models like support vector machines, k nearest neighbor, so on and so forth. To understand this with an example, you can see here, equation for standardization goes something like this, which is called z-score, which is equal to the each input, which is x, minus mean of x divided by standard deviation, which is calculated from all the input variables. Let's understand this with example. So this is the column given, where you can see the different prices ranging from 20 is the minimum one and 200 is the maximum one. And if you calculate a mean of these prices, that comes up to be 79. And if you calculate the standard deviation, that comes up to be 51. And let's try to put these values in the equation given here so that you will able to get the z-score, which is nothing but the standardized value. And when I calculate z-score, these are your new scaled prices. So what we did here, we are calculating z-score for all the variables. Let's say for 100 minus mean is 79, which is 21 divided by standard deviation 51, right? So 21 divided by 51, the value which comes up to be 41. So if you do the same thing for all these variables, these are the values you're gonna get. If you do it for the last variable, let's say 200 minus mean, which is 79, 200 minus 79 is 121, right? And divided by standard deviation, which is 51. So 121 divided by 51, which comes up to be 2.37. So this is how the standardization is done for all the variables by using this equation. What's the benefit? Standardization centers the mean to 0. This is important. Scales the variance at 1 and it preserves the shape of the original distribution. Minimum and maximum values will vary and preserves the outliers. You'll understand this with the help of demo. So let's jump to Jupyter Notebook now. Let me open this Python book with a Jupyter Notebook. So this is where we are now. Feature scaling refers to the method or a technique used to normalize the range of independent variables. And what are the different ways, the techniques? We have already discussed this in the previous video. We have also seen how to calculate the z-score, how to standardize the values. Now let's see how to perform the same. The very first thing that I'm gonna do is import thumb up rule, right? So first thing, do the imports. Pandas, matplotlib, dataset. We're gonna use California housing dataset for this. And to split the data into train, test, split. And importantly, the scalar, standardization scalar, sklearn, pre-processing, import, standard scalar. We'll be using standard scalar for this demo. Let's execute this. Now let's load the inbuilt dataset using fetch California housing into X and Y. And let's print the head, the first 5 rows. Alright, this is how the data look like. Median INC, house age, average rooms, average bedrooms, population, so on and so forth, right? So here, I don't really understand if data is in between 0 or 1. So here you can see the vast range of data, right? So data has a variance, and to understand this variance, let's describe the data so that I understand the statistical parameters of these variables and I also get the idea of magnitudes here. So I'm going to use x.describe and round it to 2. Okay, so this gives me count, mean, standard deviation, minimum and the maximum value, right? Definitely mean is not centered at 0, right? This is before performing standardization. And the variance is not also 1, right? So variance is huge for population especially. And this is where we need the standardization. Alright, so let's perform standardization to get the mean values to 0 and standard deviation to 1. So these two values we should get 0 and the standard deviation in between 0 and 1, right? Let's do that. So very first thing we are gonna do is split our data into training and testing. We need 70-30. Test data is 30%, train data is 70%. Let me see the shape. So I have these many number of rows and 8 columns. Let's perform the standardization on this data by using standard scalar, right? So we imported standard scalar here at the top from sklearn library. Initialize standard scalar and keep the data in the tabular form. So that's why I transform pandas, fit the scalar to train our model. So scalar.fit to perform the standardization. So initialize, fit, and then find the accuracy. This is what we do in machine learning, right? Initialize, then fit the data, and then finally use transform, scalar.transform xtrain, scalar.transform xtest, right? So these are the new values after performing scaling. Okay, so let's see what are the output we are gonna get. So some of the important variables under scalar you can see here. So if I do scalar.mean, I'll able to get the mean for all the columns here. You can see these values as arrays. I can also see the standard deviation. Scalar also stores the deviation. So scalar.scale, if I do, I'll able to see the standard deviation for every feature. Okay, and finally let's describe after scaling, right? So this describe I am using on scaled data set, right, after performing standardization. So let's describe now. I should get mean to 0 and I want the standard deviation as 1. So am I getting the standard deviation 1? Absolutely. So do you see that this is the difference after performing standardization? You see mean to 0, standard deviation to 1. And before performing standardization, you can see mean is not centered and deviation is also ranges between different numbers, isn't it? But the question is, will this disturb the characteristics of the data? Will it disturb the distribution of the data? We also discussed that in the previous video. Okay, let's see the distribution of the data before scaling. So this is before scaling. What is the distribution? This is how it looks like. And let's see the distribution on the scaled data. So this is where we have performed distribution on the scaled data. You can see it's something like this. And if you compare these two distributions, there is no difference. If you observe 0 to 2500, just observe visually, right? And there is no change in the distribution, right? Whereas their means are changed. It starts with 0 to 15, 0 to 40, and for latitude, longitude, this is something different. But after performing scaling, the mean for all the variables starts with 0, right? All features become data centric, right? Even for latitude and longitude without changing its distribution. So what's the standardization effect? You can see here the mean before standardization is 79, but after standardization mean is changed to 0. And you can also see the variance. It is 2589 and standard deviation is 51, but after standardization mean is changed to 0, variance changed to 1, and standard deviation is also 1. That is the benefit of doing standardization. Okay, now let's talk about the second type in feature scaling, which is normalization. So normalization is another star player and this is widely used. So normalization squashes your features into fixed range between 0 to 1. You can define the range, but generally it is 0 to 1. Default is 0 to 1. So this is handy for algorithms that don't like huge outliers, such as some tree-based models and neural networks, right? So in simple words, normalization scales the variables between 0 to 1, okay? And this is how the equation for normalization looks like. X scaled, which is nothing but the values after normalization, performing min-max scaling. Each variable, which is input value x minus minimum of x, that is input, divided by max minus mean. Let's see the example here in the diagram. So again, we have prices given here in the column, right? Prices ranges between 20 to 200. Minimum is 20 and maximum is 200. And let's calculate the max is 200, minimum is 20. So the range becomes 200 minus 20, which is 180. So in the denominator, we need the range max minus min, right? Which is 200 minus 20, which is 180. And the actual variable minus minimum of input, which is nothing but here 100 minus 20, which is 80, divided by 180, which comes up to be 0.44. So this is how the values are getting calculated. Let's perform this for 20. So if I perform it for 20, 20 minus minimum 20, 20 minus 20 is 0. This 0 divided by anything is 0, right? So that's why for 20 you see it is 0. Let's see the scaling for maximum value, which is 200 here. So 200 minus minimum, which is 20 again. So 200 minus 20 is 180. So 180 divided by 180 is 1, right? So for 200, the value becomes 1. And that's how min-max scaling works. So take away from this, the minimum and maximum value is between 0 and 1. Unlike standardization, mean can vary here. And also the variance can vary. Unlike standardization, in standardization, mean remains constant, but here mean varies, right? Let's jump for the demo so that you understand in a better way. So again, here back on the Jupyter notebook, min-max scalar, that is normalization, squeezes the values between 0 and 1. This is the equation to calculate mean max. We already discussed it. So let's go for the next cell. We are doing the imports the way we did before, right? Same dataset, fetch California housing dataset to split the data into train and test. And the important statement is this, where we are importing mean max scalar from sklearn.preprocessing. Okay, let's load the data into X and Y using fetch California housing. Now let's describe the values. With the help of describe, I'll able to understand the statistical parameters of these variables, right? The way we did it for standardization. So I need to see mean, standard deviation, minimum value, maximum value, 75% of each value, so on and so forth, right? So here you see minimum value and the maximum value is quite different for each feature, right? Same for maximum, right? So the values are different. Remember, we are performing normalization here. So we are not looking for mean and the standard deviation, but we will be looking for minimum value and the maximum value. In normalization, mean can change and also the variance can also change. So we want to observe these mean value and the max value. So now let's perform standardization. Split the data into train and test, then perform min max scaling. We have initialized min max scaler here. Fit the data and perform the transform. So we are using one simple method which is transform here. Scalar.transform, xtrain, scalar.transform, xtest. If you want to see the maximum value and the minimum value, you can use scalar.dataMax. These variables store the maximum values and min underscore scores the minimum value. So these are your maximum and these are your minimum values. You can also see the range, data range, which is nothing but max minus minimum, right? And now the important thing that we need to perform is describe. Now let's describe the data to see the statistical parameters of every feature. And we are performing this time on the scaled data and not on the original data, okay? So this is our scaled data after performing scaling. So this is our original data after performing scaling. Let's see how does the data looks like now. So if you see, mean is not set to 0, unlike standardization. In standardization, mean set to 0. And standard deviation is also varies. Standard deviation in case of standardization, it is 1. The important point that we are looking for here, the minimum value and the maximum value. So if you see, minimum value is 0 in every feature and the maximum value is also 1. So minimum and maximum range is in between 0 and 1. So if you see, every feature which you see here is ranged between 0 and 1. Amazing, right? And let's see the histogram just to see the distribution. So this is on X train before performing scaling. Look at the distribution, right? And this is after performing scaling, that is normalization. Okay, the distribution doesn't really change. The important thing that you need to note here, the value ranges between 0 to 1, 0 to 1, 0 to 1. For each and every feature, values are squeezed between 0 to 1, right? This is the reason why we use normalization. Distributions doesn't changes, but we keep the values in between certain range to normalize their magnitudes, right? Now let's perform the same thing on the real data sets so that you can practically visualize and practically see what happens after standardization and normalization, okay? So we are performing feature scaling on the wine data set here. And to do that, I'm importing wine data, right? pd.read csv. The data set is available under this directory, and let's see the head. Okay, so we are looking for only 3 columns currently: class label, the type of wine, alcohol content, and the malic acid content. Alcohol content and the malic acid content here. All right, now let's apply the standardization on this data by using pre-processing, standard scalar, fit, alcohol, and malic acid. So I want to perform standardization and also do the training on both the columns, alcohol and the malic acid, and finally perform the transformation by using transform function here. So what we are looking for here is mean after standardization. If you see, mean after standardization becomes 0, 0 for alcohol and malic acid, right? And we also want to see the standard deviation after performing standardization. So the standard deviation becomes 1, right? Mean to 0, standard deviation is 1. That is the effect of standardization. We have been talking about this again and again. Now let's perform min max scalar as well. Wait till the end, we are going to visualize this as well, okay? And to perform min max scalar, I have initialized min max scalar, perform data.fit, alcohol and malic acid, and finally again use transform. Nothing different. In min max scalar, we are interested into minimum value and the maximum value and not the mean and the standard deviation. We are looking for minimum value and the maximum value here. Okay, so minimum value is 0, 0 and the maximum value is 1. Beautiful. The difference we are going to see after plotting. So you will able to see here how does the data look like before performing standardization and after performing standardization on the same data, and also after performing min max scalar. Okay, so let's plot the data. So we are plotting scatter plot here. Okay, if you observe, we are plotting the scatter plot For the original data set first, DF alcohol, DF malic acid, we are plotting a scatter plot again on standardized data, and we are also plotting a scatter plot after performing min-max scalar. So we should have 3 plots on original data first, after performing standardization, and after performing normalization, which is min-max scaling. And let's add the title, labels, legends, and plot the data scatter plot here. If you see, this is a really wonderful plot I can see here. Let me zoom out a bit so that you can see it properly. If you see green one, which we have plotted, color green, right, on original data set, if you see, this is where you can see the scatter plot. The mean is not at 0, the values are not in between some specific range, and the scatter plot looks somewhere away in the plot, right? So this is how it looks like without performing any scaling. But if you see the pink and the blue one, after performing standardization, mean became 0 and deviation became 1, 0 to 1, 0 to 1. This is the effect of standardization. These are same data sets. These are not different data sets, okay? So we perform scaling on the same data sets here. But here we are visualizing it just to understand their nature. Their nature doesn't really change. Distribution doesn't really change. After performing min-max scaling, you can see 0 to 1. The value ranged between 0 to 1 on x-axis and also on the y-axis. That's the benefit of performing feature scaling. Beautiful, isn't it?
And that's how we come to an end of this video. If you have any questions regarding the same, let us know in the comment below. If you found this video helpful, please subscribe to my channel and hit the like button, and don't forget to share this video with your friends and the colleagues. Thanks for watching. See you again next time. Till then, take care and bye bye.